Okay, so good afternoon, everyone. Welcome to Lecture 4. This is going to be on amplifiers, and this should be review for a lot of you, although there could be some of you, depending on which 16 you took, where some of this might be new. Again, if this is new material to you, then I'm going to go somewhat quickly through this because it's review for most, but a lot of this is in the book as well, so you can read some of those sections from the book to get a better understanding of this too. So just a couple announcements before we start. So first, homework number 1 you know is online. That's due next time, which is this Friday. Lab number 1, the pre-lab, has been online. And if you've started that, that's great. You got a real good head start there. But we're actually going to have a change of plans regarding the labs. And so basically what we were going to do is that next week we would have started the labs, but Monday was a holiday, so it would be the Tuesday lab section that starts. And then you'd have to wait almost a whole week for the Monday lab section to get to that. And so that didn't make a lot of sense. It's better to keep the two labs together, at least from the perspective of the material that's been covered in the class by lectures and homeworks, etc. It's better and fairer that way. In addition, you won't get your lab kits until probably the week after next, and some of you may not even get it by then. So it makes better sense to not start the labs next week, mainly to keep them together, the Monday and Tuesday labs together. And so we're not going to start the labs until Monday, 9/14. So September 14th is when the start of the labs will be. You already have your pre-lab 1. You have much more time to get that done. Some of you already have a lot of it done, which is great. But if not, you have 2 weeks to do that. And I think that's most of the announcements that I have. I guess the class is pretty much full. Last time I checked, there was 1 slot left. And so if you know anyone, they can get that 1 slot. We're not going to be sending out your lab kits until the end of this week. But hopefully you've sent in your information to that Google form, and we have it so that we can start sending those out. Any questions about anything logistically about the class? Let's see, David is asking if you can remind the students. Okay, yeah, I just did that. Okay, so according to the chat, we're missing about 6 of those Google forms. So if you have not filled that out, please do that today if you can, because we're going to start sending these out on Friday. And you're going to want to be on that list if you want that lab kit, which means if you want to take this class. Seeing nothing else on the chat, lecture topics today are going to be continuation of what we were doing last time, which is sort of starting to get into BodePlots. And so I will teach you how to do BodePlots. I guess some of you know how to do that, some of you don't, depending on the 16 you took. We'll then talk about amplifiers, which I think all of you have seen from 16, maybe in different degrees. We'll talk about amplifier models, 2-port networks, input resistance, output resistance, and then an ideal voltage amplifier. We might get to op amps, but I doubt it. That'll be the topic for the next lecture. But for right now, let's start from where we were last time, which was sort of going through the procedure for doing a BodePlot. And sort of the last thing we did last time was do the BodePlot for an all-resistive network like this voltage divider. And for that case, the magnitude is, which is basically V0 divided by VI as a function of frequency. That's constant with frequency. And the phase is also constant with frequency and is 0 because we have no energy storage elements there. There's no capacitors, no inductors. Once we add reactive or energy storage components like capacitors and inductors, what this does is it starts shaping the frequency response. And it adds singularity, so it adds poles and zeros, and it yields the general transfer function that I wrote last time, which is right here. And from last time I was using J right here, but I changed it to K so as not to confuse it with the J that I'm using for the imaginary number. But anyway, this is our general transfer function. It's not going to look like this when you see it. It's going to look like a polynomial. So it'll have some polynomial in the numerator, some polynomial in the denominator. That's going to be multiplied by this H0. This H0 is basically our resistive term. That's the term that we get if we just had a bunch of resistors. But if we have a bunch of resistors and add some capacitors or maybe some inductors, then we would get this term here, which is our frequency shaping term. So let me just call that what I just said. That is our frequency shaping term. And this first thing is our resistive term. Whoops. The resistive term has no frequency dependence. And so sometimes I'll call that the DC term, like the direct current term or something here. But nevertheless, your transfer functions will pretty much always look like something like this. You'll have some S terms and some terms without the S. And so these are all factors right here. So this is what it would look like if you factor your polynomial, and that's what you'll do before you are about to make a BodePlot. So get it in factorized form like this. Again, everything on the top of this, the z's here, these are zeros. And so why do we call these zeros? Well, a simple answer is that if I make this term 0, say if I make s equal to z1, that goes to 0 and the whole transfer function goes to 0. So it makes sense to call that a 0. Anything at the top, any of these factors at the top, the z's are zeros. These at the bottom, the polynomial in the denominator, these are poles, the p's there, because if I set s equal to p1 here, that will make this 0. And if it makes this 0, this will shoot to infinity. Okay, and you can think infinity is like a delta function, which is kind of like a pole. So that's a good mnemonic way to remember zeros and poles. Right? The zeros are in the numerator, the poles are in the denominator here. And so in general, the z's and the p's, the zeros and the poles, are complex numbers. And so, for example, z sub k, which I've got out here, is going to be sigma z sub k plus j omega z sub k, where the real part of this complex number obviously is this sigma z sub k, and the imaginary part of the complex number is omega z sub k. I could say the exact same thing for the poles. So p sub I is sigma p sub I plus j omega p sub I, and etc., pulling out sigma p sub I and omega p sub I. This is a transfer function of the output signal divided by the input signal, and so this is the input variable, that's the output variable, and I'm drawing them as V, but this is not necessarily voltage. They could be voltage, they could be current, they could be velocity, they could be force if you're working in mechanical domain. So a lot of the things that we talk about here, we are going to talk about them in the context of electrical engineering, which means voltages and currents, but keep in the back of your mind, if you ever take a MEMS course or a mechanical engineering course, that all of these concepts that we're learning are also applicable to other domains too, like the mechanical domain. And so given a polynomial transfer function like this, we can then generate a BodePlot. And so I think some of you have done that before. Some of you may not have done much of that. And so we're going to start from the basics on exactly how we go about doing that. And I'm going to start doing that on the left side here. And so let me title this BodePlot. Okay, so in a BodePlot, what is this? This is one. You want to make a plot of the magnitude in a decibel scale. So we want to plot magnitude in decibels. Which is dB, versus log frequency. Okay? And I'm then going to want to plot the phase versus log frequency as well, but let's handle the magnitude first. So we know that our h of s, which is the same as h of j omega, if I wanted to take the magnitude of this, I would then end up, if I was using this transfer function from before, so here on the right, so that same transfer function, the magnitude, is then just going to be the product of all the magnitudes of everything, of the factors in the numerator, and divided by the product of all the magnitudes of every factor in the denominator. So I'm going to write this out here as this pi from k equals 1 to m, magnitude j omega minus all of my z's, so my z sub k's, divided by product of I from 1 to n, j omega minus all of my poles, p sub I. Okay? Shorthand way for saying that I'm taking the product of all those magnitudes. So I know those magnitudes, or I can derive those magnitudes. Let's go ahead and do that. Let me go down here and say that this then is going to be equal to h naught times still that product, k equals 1 to m, of, and now I'm going to plug in what z sub k is. So z sub k is just this sigma zk plus j omega zk that I have on the right there. So I'll plug that in, and I can write this then out as j, and I'll move some things around algebraically. So j times omega minus omega zj minus sigma, zk, minus sigma zk, that magnitude, divided by the product of all of my pole magnitudes. So that's going to be j times omega minus omega pi minus sigma pi. Okay? And so I'm basically expanding this, and you know how to take magnitudes. To get the magnitude of something, you just multiply by its complex conjugate and take the square root of that. So doing that, this will become h naught pi from k equals 1 to m of square root omega minus omega zk squared plus sigma zk squared. And then in my denominator, I equals 1 to n square root omega minus omega pi squared plus sigma pi squared. Okay, so that's our magnitude here. And this magnitude is requiring us to take the products of several things and dividing it by the products of several other things. Most of us don't do well, especially when graphing, having to take products of things and multiplying graphs together. We do better adding them together. So that's why we like to convert this to dB. Okay, so we're going to take this and we're going to convert to dB, because what that does is allows us to combine things by addition. Oops. So it allows combination by addition rather than products. Okay, and the reason why we want to do that here is because we want to make a BodePlot. And for a BodePlot, since what we're doing is making a graph, this becomes much easier to graph if we just do this. And so, you know what decibels are. That means we're going to take 20 times the log of our amplitude, or transfer function's amplitude. And so that then is going to reduce, if I use one of these forms up here, let me use the smaller form, this one here, so that things aren't cluttered. So this is going to then be 20 times the log first of h naught, all by itself, and then plus everything that's in the numerator, so plus k equals 1 to m of 20 times the log of all of these magnitudes, then j omega plus z k's. Okay, and then minus the sum from I equals 1 to n of 20 times the log of all of the magnitudes of the factors of poles. So magnitude j omega, this should be a minus, sorry, minus z sub k, and minus p sub I. Okay, so that's how we're going to be handling the magnitude part part of a BodePlot. So this is just expressing it in equation form. It's basically saying that if I can find the magnitude plots of each of the factors, then all I have to do is add them together, right? So for the BodePlot, just add the magnitude plots of the zero factors and subtract those of the pole factors. So that's in words what I'm going to demonstrate later on in this lecture. Okay, so but before doing that, let's go here and let's now talk about the BodePlot for the phase. So 2, for a BodePlot, it's not complete with just the magnitude. You also have to plot the phase versus log frequency. And so in this case, our phase, I don't know why this thing does that. I guess I do know why it does it, because at the bottom my hand is touching that. But nevertheless, the phase of h of j omega is going to be equal to the sum from k equals 1 to m of all of the phases of the factors which I've been calling the zero factors, all the factors in the numerator, minus the sum of all the phases, so I equals 1 to n, of all of the phases of the factors in the denominator, which are the pole factors. Okay, where each of these factors, the phase, which I'll just say the phase of j omega minus an s, where s in this case I'll just say is equal to sigma sub s plus j omega sub s. Okay, this is just going to be equal to the inverse tangent of omega minus omega sub s divided by minus sigma sub s. Okay, so all of these things you should have seen in a previous class, but what this is saying here is that we're just adding all the phases. Okay, so for BodePlot, you add the zero phases and subtract the pole phases. Or when I say zero phases, I mean the zeros, the factors that have the zeros in it, and poles, the factors that have the poles in it. And so what I want to do is demonstrate this actually, but before demonstrating this, let me talk about something that you may or may not have seen, and that is the complex plane. Okay, this is not something you're really going to have to understand in great detail in this class. Your book does talk about this, so it's a good thing to know. But I thought, and I don't usually talk about this when I teach this class, but I think it's a good thing to know, at least know right now, because if you go on to take something like 140 or 128, you'll start talking about this quite a bit. And so the only reason why I want to show this is that this sort of gives you a geometric description of what all the stuff on the right, what all the math on the right that I showed there, this gives you a geometric way to think about all of that. So if you look at what is here, this is a plot of this S, and it's got the imaginary part of S plotted against the real part of S, where S is that complex variable again. And so what you would do in the complex plane is you'll take the poles that you have and the zeros that you have and actually plot them in this plane. And so if I have a pole, say one of these poles in this, go back here, in this. So say one of the poles right here is equal to, say, sigma 1. Okay, then I can plot that in this plane as sigma 1, 0. Okay, if I have another pole that's sigma 3, then there's the pole there. Poles are x's and they're red in this plot. If I have a 0, which means something in the denominator here, like say this z1 here was equal to sigma 2, then I can plot sigma 2 as a 0 here. And you can see that these are all real poles that I'm using as an example. I could have an imaginary part like this j omega zk that I'm showing on the right side, but I'm keeping it simple and not doing that. And so geometrically, what you see from a plot like this is if you go to a certain frequency, and so this axis imaginary of s is the frequency axis, so everything on here is omega, and so for example this point is equal to 0 on this axis and omega right here. So omega is right there where I'm pointing, and so for that particular frequency, each of these poles and zeros makes a line to that point. And each of these lines corresponds to the magnitude. The length of the line corresponds to the magnitude contribution from, say, this pole right here. And so that would be the length of this line, and from your trigonometry or geometry, you should know that the length of this line here, since it's really just the one side of a triangle here, by the Pythagorean theorem, it's just omega squared plus sigma 1 squared under the square root. And that is exactly what the magnitude contribution would be from a pole in this transfer function at the right. Okay, so what this tells you is that the lengths of all of these lines here correspond to magnitudes. The angle that these lines make with the x-axis corresponds to the phase of this particular pole. So this pole is contributing this magnitude and this phase to these sums that we talk about, this sum of magnitudes and this sum of phases. This 0 is contributing its own length, magnitude, and its own phase to the whole thing. And so what you do graphically here is you just add up all of the phases, you multiply out all of the magnitudes, which ends up being like adding when they're in decibels. And so in the end we get the exact same equations that I've written here, but you can just look at it from a graphical fashion here. Okay, now if that was too much for you, because I'm doing this very quickly, and it could be too much for some of you, you can look in the book, and they do discuss this. This is, again, not something that important for this class. I just wanted to expose you to it so that if you get to 140 or 128, you'll at least be able to recognize it and say, oh, okay, yeah, I saw something like that in 105. But we may never talk about this again. I just wanted to make sure you saw this, at least in this class for once. And so now let's move on and now talk about, get back to what we're really trying to do, which is to do a BodePlot. And I'm having trouble keeping this on the same page. Okay, so because everything reduces to addition, for both the magnitude and phase when we're doing things in decibels, okay, you can determine the plot for each term, then add and subtract them together. Okay, basically that means we can use superposition for both the magnitude and phase plots, and that will simplify what we have to do very much here. So now let's go through actually doing an actual BodePlot. So here's a step-by-step procedure. So get all the factors into the form s, or 1 plus s over a. That's the first thing you want to do. So for example, if you had something starting with s plus b, you had a factor s plus b, factor out the b so that you end up with b times 1 plus s over b. That's the first step in the BodePlot. I guess the step before that is if you had a polynomial, you factor it into factors in the numerator and denominator. Then you plot the BodePlot for each factor, one factor at a time. And note that there are only a few cases for this. So you can memorize all the different cases if you want. We'll talk about those cases in a second. You then sum all the decibel magnitude plots to obtain the total magnitude plot. And you then sum all the phase plots to obtain the total phase plot. Okay, and so that's the procedure, step-by-step procedure in words. Of course, words are just words. Let's actually do it to demonstrate how this can be done. So let's use this example here for our demonstration. So I've got this example of this polynomial that I've already factored at least this far. Do 100 times s times the quantity s plus 10 to the 5th divided by quantity s plus 10 divided by quantity s plus 10 cubed. Right? So at the top are the poles, at the bottom are the zeros. So the first thing I want to do if I want to make a BodePlot is factor this. Okay, so let's go ahead and do that. So to factor this, so I want to factor it first to pull out my DC term, and then I'll have another term that's my frequency term. So I'm going to have 100 right here because I already have that 100 sitting right there. And then I'm going to factor out this 10 to the 5th, so I can turn this into this form up here. I can turn this into this form up here. Okay, so I'm going to pull out 10 to the 5th, and I'm going to end up here on my frequency side with s times 1 plus s over 10 to the 5th. Okay, perfect. That's what I want. That's the numerator. Now the denominator, I'm going to want to pull out this 10, and I want to pull out this 10 cubed. And so here they come, 10 and 10 cubed. And then what I'm left with s terms is 1 plus s over 10 times 1 plus s over 10 to the 5th. Okay, so now I have this in the form that I like. So this term right here, this is what I called h naught before. And if you multiply all this out, that's just 10 cubed. This is what I call my resistive term. I'm also going to call it my gain term. So I'm going to go ahead and call it my gain term here. Because as you'll see later on, this is like our DC gain. This thing right here is what I called before, and that what I will continue to call throughout this course our frequency shaping term. Okay, it has the s's, which has the j omegas. And so it is a thing that's going to shape our frequencies here. Okay, and so what we found is that factoring brings out the gain term. Which is something we want. Okay? And the gain term, that's a constant value. Right, so that's one of our cases. That's actually the case that we looked at before. So if I go back here to the very beginning of this lecture, right here. This part right here, this is a constant gain. And so this is a constant gain BodePlot. And so this gain term here is one of the cases that we have to memorize when we do a BodePlot. And so this is the case where we have a constant value, or a constant gain. And so when we have this constant value, what this means is that we have a constant amplitude, obviously. And that, in decibels, is going to be 20 times the log of h naught. In this case, it's going to be 20 times the log of 10 cubed, which is equal to 60 dB. Okay, and then we also know that if we have a constant value, constant gain term, then this will have a constant phase, and its phase contribution is going to be 0 degrees. Okay, that's one of our cases that we've already looked at. But, of course, there's all of these cases here in this frequency shaping term. I've got a bunch of factors there, and I now need to be able to plot the BodePlot of all those factors. So let me go to the left side here, and here are all the different cases here. So here is that same transfer function, except I've replaced all this with that 10 cubed. Everything else is the same there. And now what I want to show is that each of these factors in the frequency shaping term has its own BodePlot. And you're going to see these again and again and again. So you only have to memorize these cases that are on this page right here. So the first case you need to know is the case where you have S all by its lonesome. Okay, that means that the factor, which I'll call A of S, is just equal to S. What that is when you plot the BodePlot, so this is A versus omega, and I guess I should be clear here that it's A versus omega, where A, A is in dB, and omega actually in all these plots are log omega, or a BodePlot. Okay, so if I'm plotting that, then in this, with these axes here, what I'm going to get is a straight line going through 1, and at 20 dB per decade going up. Okay, the magnitude will be like that. And for this same case with just S, which is a 0 at the origin, right, the 0 is at 0, well, the 0 is at 1, frequency of 1. Okay, let me go back to what I had there. This actually is frequency because I'm using 1 there, and I want to continue using 1, so let me not put the log on that there. Let me just keep that as frequency. And let me fix that green thing. Okay, so in this case, the phase of this is going to be plus 90 degrees all the way through. Okay? And so now, that's the case for S. For this case, if I have 1 plus S over something in the numerator, this is now a first order 0. So this is where A of S is equal to 1 plus S over something. I'm calling it B here. In this case, it's 10 to the 5th. But anytime you see this, 1 plus S over B, in the numerator, then the BodePlot looks like what you're seeing here. It's actually flat coming up to B, and then after passing B, it goes up 20 dB per decade. Okay, these are just what the plots look. I think all of you have probably done at least this much plotting in your previous class for BodePlots. That's why I'm not going through this in great detail here. But when you make a plot like this, what you usually do is you create asymptotes. See the blue dotted line here? So the asymptote coming from low frequencies before I get here is just a straight line, that dotted line. Beyond B, the asymptote starts going up. And you can see that the actual curve, which is in red here, actually does not intersect the corner of my asymptotes. It's actually higher than the corner of my asymptotes. And how much higher is, you can just plug in here. So in this case, that's at omega equals B. That means S equals B here. This is basically like 1 plus 1. All right, except you're taking the magnitude of that, so that's the square root of 1 plus 1, or the square root of 2. That means in dB, that's 3 dB up from this position here. So I can go here and I can say that the actual position is 3 dB higher than the low frequency asymptote here. Okay? Let's see. I'm looking at the chat right now. Someone asks, is the next step rotating and stationary phasers? Yeah, you can. When I talked about the complex plane, you could start thinking about rotating and stationary phasers as well, but we're not going to go into that in this class very much. You can think of it that way. There are other classes that will definitely think of it that way. But proceeding more with this, that's everything in the numerator. For things in the denominator, like this 1 plus S 10 to the cube, that's of the form 1 over 1 plus S over A. And so in that case, same thing, I have that asymptotes, a low frequency asymptote that's a straight line that goes all the way up to A. Then high frequency, it goes down now 20 dB per decade, because this is now subtracting or dividing this transfer function. And so same thing, then I draw my actual curve 3 dB down from the actual corner of this thing, so I can then come out here and say that's also 3 dB right there, that distance there. Okay, and then another useful case, and for the phase of this, I missed the phase of the poles. Let's go back to the pole here and let's talk about the phase. That's a big thing to miss, because I think a lot of you have done the magnitude, but some of you told me that you've never done the phase before. And so how do you go about doing the phase for this transfer function right here? Well, in order to do the phase, we could sort of go back to these equations that I wrote for phase. So this right here. And so if we're looking at this here, if I have a phase that where the input to this, where the frequency is very small. So if I have a very small frequency in this, for this 0, right, then I'm going to have minus omega s over this minus sigma sub s, and sigma sub s is going to be a negative number because it's going to be a negative 0 usually for stability. Then this will be positive here. This will be the inverse tangent of a number that will make this 0, right? So that'll be the tangent of 0 becomes 0 right here, right? So we're going to have 0 phase to start out with. And then by the time we hit the end of this, we're going to end up with plus 90 dB in phase. And so this ends up here at plus 90 dB. well, sorry, plus 90 degrees. And so you're seeing how I'm building up this phase. When I get to B, the phase at B is going to be plus 45 degrees. And this is all just from this equation back here, this inverse tangent equation here that I'm sure you've played around with before as well. That's going to be 45 degrees. And so that tells you to make this phase plot, all you have to do is draw an asymptote that when it goes through B is at 45 degrees, the frequency B. But at very high frequencies, it's all the way up at plus 90 degrees. And so at high frequency to me means 10 times higher than B. At a very low frequency, it's going to be 10 times less than B. That's what I'm considering a low frequency. And so usually when you draw the phase plot, you'll draw an asymptote that is just 0 all the way up to B over 10. And then you'll draw the asymptote that's plus 90 degrees all the way up to 10B. And then you will just draw a line between these. And that then becomes your asymptote that helps you draw your phase plot. And so when you draw the phase plot, this is what it'll be. Is it log omega then? Yeah, it is log omega. So the other way to do log omega is to just write omega here, but then your scale is like a log scale. You go by tens. And so what I have here is correct. I've got omega here. But I'm plotting log omega because I'm not doing B plus 1, B plus 2. I'm doing B over 10, B, 10B. Each of these marks here is 10 times the previous mark. Right? So the scale is log that I'm drawing, but I'm not writing this as log omega right here. This is omega. These are really omega values, but the scale really is a log omega too. I hope that makes sense what I just said. I'm trying to answer one of the chat questions there. Okay, and so same thing for the pole. So for the pole, this was for the 0. And so for the pole, same thing. You find the pole location, 10 times that location, 10 times, or that location divided by 10, create your asymptote, then draw in your phase. Okay, and in the end, we're going to add all these things together. But before doing that, let me do one more useful case. So in this transfer function that we have up here, we have pretty much all the cases. We got this s by its lonesome. We have this 0. We have these poles. What we don't have is an s in the denominator by its lonesome. Okay, so if I have an s in the denominator all by itself, then that's going to be the case of a pole at the origin. And so that would be a pole at 1, at frequency 1. And you're just going to have a straight line going through that at minus 20 dB per decade, and its phase is going to be minus 90 degrees. And so in this plot, I guess looking at it, it's a little confusing, so let me say this is 0 degrees there. And that's at minus 90 degrees. And for the pole, I guess I'm missing my minus 90 degrees here too. Minus 90 degrees, that's 0 degrees. And to be absolutely complete, let me also put a 0 degrees right there. Okay. Any questions about, okay, I'm looking at the chat. No questions right now. So these are your basic cases. And so from these basic cases, we're going to use these to plot the whole BodePlot for this transfer function now. So let's focus on this transfer function here. Let me move on a couple slides until I get to my nice plots. There they are. All right, so what we're now going to do is plot the magnitude and phase BodePlot for exactly this transfer function. And so what I have to do is plot the BodePlots for each of these factors. Okay, so I want to first plot the BodePlot for 10 to the third. And so my BodePlot for 10 to the third, well, let me define my axes first. So this is, I'm plotting the magnitude BodePlot first. Let me make this black. So I'm plotting h of j omega, and in units of decibels. Okay. And so I'm going to make this 0 decibels here, make that 20, 40, 60, 80, and going down here, right, this will be minus 20, etc., minus 40. And then on my frequency scale here, I want to plot log frequency, but I'm just going to note this frequency, and I'm just going to put my numbers on this here. So let's make this 1, make that 10, make that 100, make this 1,000, 10 cubed, 10 to the 4th, 10 to the 5th, so on. I'll go all the way to 10 to the 8th. Okay, and so that's my frequency scale there. And so now let's do our magnitude plot. So the first thing that I want is to plot this 10 cubed. Right? So it is just a resistive term. It's a gain term. It has no frequency response. So for that 10 cubed in the magnitude, it's just going to be this. Okay? And that's what I'm going to add to everything else. But I can't add yet because I've got nothing else to add it to. So let's go to the next term here, this S term that's in the numerator. So this S term, like we said, that's a first order pole. Or sorry, that's a 0 at the origin. Okay, and so it's going to have a Bode plot like I'm showing in blue on the left side. And so let's also make that blue on the right side. And so that's going to go about 20 dB per decade. And so I'm going to go ahead and put its asymptote in here. And it stretches even down this way here. So that's what corresponds to the Bode plot for S. And this first thing that I plotted, just to be complete, is the Bode plot for 10 cubed. Okay? And so now I want the next term. I want this 1 plus S over 10 to the 5th. And so for that, let's make that green since that's a pole. Okay, and so that pole is at 10 to the 5th. And so if that's at 10 to the 5th, then I'm going to have to go all the way out to 10 to the 5th right here. And that's when it's going to start going down. So this asymptote for this pole actually is doing this. So you see the green dotted line that I'm coming up all the way to 10 to the 5th. Then I'm going to start pulling this down 20 dB per decade after 10 to the 5th. And that's my asymptote. That is for the term 1 over 1 plus S over 10 to the 5th. Okay? And now I've got this final term here, 1 plus S over 10 to the 3rd. It's going to be the same thing, except now I'm going to start coming down 20 dB per decade at 10 to the 3rd. So that becomes this. All right, so here that's 1 over 1 plus S over 10 to the 3rd. See if I can make that look like a 10 to the 3rd. There you go. Okay, so those are all the components of my magnitude plot, and what I have to do is add the 0 plots and subtract the phase plots. Okay, so let's start doing that. So let's go right here at the very beginning, at this very low frequency, right? This is not 0 frequency here, this is 0.1 frequency on the axis here. And let me do the final plot in black, since that'll show up against anything else here. But right, I start out with 60 dB, but this first 0 at the origin is pulling me down 20 dB. So where I'm really starting is at this 40 dB right here. That's my starting point right here. And that's going up at 20 dB per decade. Right? This thing is going up at 20 dB per decade. And so what I really want to do is draw an asymptote here. It keeps going up 20 dB per decade until I run into... Okay, what did I just do? All right, I'm sorry, I screwed up. For some reason, I was thinking that this 10 to the 5th was a pole. It's not. So this part that I just did is wrong. I was looking at the wrong part. Let me backtrack this. That 10 to the 5th was a 0. And so I got to fix this here. Someone said something about that? No one said anything. Yeah, okay, there's someone did say it. Kristen Pella said that. You saw that. Okay, so that was a 0. And so 10 to the 5th, I should have gone like this, all the way out here to 10 to the 5th. And that went out here. And so this 10 to the cubed is really a pole. But I have another pole at S equals 10. Okay, so this goes out here. So I actually was looking at a different transfer function. In my notes, I have a different transfer function than what I have here. So I was plotting something else. So now with this pole at 10, now I'm going down this way. So I labeled them correctly, but let's now plot the correct transfer function. And so this, and let me move this to the other side so you can see it more easily. This is going to be 1 over 1 plus s over 10 cubed. And this is 1 over 1 plus s over 10. Okay? And the reason why I caught that, because I know what this thing is supposed to look like, and it wasn't starting to look like that. And so here, I'm going to keep going with this asymptote here. So I'm basically adding this line here with this line there. And so that's adding up to that point. But as soon as I hit 10, now I'm subtracting this line at 20 dB per decade. So that negates this line here. And so this then goes across and becomes something constant across there. It becomes a horizontal line until I hit my first pole, which is 10 cubed. And once I hit that first pole, that's going to start making this go down 20 dB per decade again. And it's going to do that until I hit my 0, which is going to force things back up. And so this is then going to cancel that, and that's going to force this to go horizontal again. So what I've drawn in dotted lines right here is my final magnitude transfer function BodePlot. And so I can finish that off by coloring it in, being sure to stay 3 dB below each of these corner points in my asymptotes. Okay, and then going through here, making the transition from bottom to top so that I can stay 3 dB above here. Whoops. I think my hand just shut that, yeah. My hand just shut off the window there, so I've got to bring another window in. Okay, and so finishing off the plot, there we go. And I guess I have a much... Okay, so that's what the magnitude plot looks like. Okay, so now let's go with the phase plot. Okay, phew, for a second I was like, maybe I should not be... Okay, sorry about that. Yeah, sorry about that. Again, I have another transfer function in my notes, and so I was plotting that one instead of this one right here. But now I am now plotting this one. So now for the phase plot, let's finish this one off. And so for phase, let me just label what this is. This is angle of h of j omega. And let me label this plus 90 degrees. Let me label this plus 180 degrees. And same down here, so this will be minus 90 degrees and minus 180 degrees. This is 0 phase. And same scale for my x-axis. This will be my omega scale. And so this will be 10 cubed, 10 to the 4th, 10 to the 5th, so on. Okay? And so when I want to do the phase plot for this, first I want the phase for my 10 cubed. And so for the phase for my 10 cubed, there's nothing. It has no contribution to phase. And so if I want to put its asymptote in, I can. And I guess I will. Maybe you can see the dotted line that I'm doing right along the axis, but it doesn't matter. And so for the S here, what is my phase? Well, it's immediately plus 90 degrees. And so for that S, I'm going to make that blue. And so right away, I have an asymptote here that comes from the S part of my transfer function. That's just a straight line at plus 90 degrees. For my first 0, 1 plus S over 10 to the 5th, I'm going to now have to make an asymptote around 10 to the 5th. So here's 10 to the 5th, right out here. I'm going to go 10 times below, which is 10 to the 4th, and 10 times above. And I'm going to draw in red, since that is a 0, its asymptote here. Okay? And the asymptotes away from those are just straight lines. So that's the asymptote for that 0. And so now for the pole 1 plus S over 10, I need to make an asymptote around 10. And so let me go to green. to do that since it is a pole. And so the asymptote of around 10, I'm going to go 10 times below 10 and 10 times above 10, which is 1 and 100. Draw a line between those two, and then draw straight lines outside of that. And finally, I've got one more pole at 10 to the third. So same thing, 10 times below, 10 times above, draw an asymptote across that. So those are now all my phase asymptotes. And what I have to do is just add all of the zero phases and subtract all of the pole phases for this. And so if I go ahead and do that, I can draw in an asymptote that starts out at plus 90 degrees, but as soon as it hits 1, it's going to start coming down. And so it's going to come down like this at the same slope as my asymptote associated with my pole at 10. Right, so that's that asymptote there. And so this one finishes going down, but this one keeps going down. And so this actually keeps going down here. Okay, all the way down to this point. But at that point, what happens is it stops going down, right? The green one stops going down, but then I've got a red that starts going up. And so now my asymptote comes up this way, and then it flattens out after going 90 degrees. So it flattens out here. And so in the end, my phase, I just have to sort of draw it along these asymptotes, looks something like this. And again, I'm going to put a curve around that. And finally, something like that. Okay? So this is now the phase plot. Let me be complete about my labeling here. I forgot to label some of these things. This thing here came from the 1 plus s over 10 to the 5th, 0. And then in green, this thing here came from my 1 over 1 plus s to the 10th, 0. And this one here came from my 1 over 1 plus s over 10 to the 3rd, 0. Okay? So there it is. We just did a Bode plot. I did it for a fairly complex plot. And what this is telling us, as we'll see later on, is when we try to put a signal into this, say into the magnitude, say I put a signal into 100 hertz right here. If I put a signal in at 100 hertz, it's going to get a gain of 80, and its phase is going to shift. Well, I guess its phase is not going to shift. That's the perfect place to put my signal if I want a gain plus no phase shift. But if I put another signal somewhere else, like right here, 10 to the 4th, what's going to happen is it's going to get a gain of 60 dB, and it's going to get a phase shift of nearly 90 degrees, somewhere around 85 degrees, a lag, a phase lag, so minus 85 degrees there. And so that's why we do these Bode plots, because later on it's going to tell us what kind of output we get out of the amplifier that we're looking at. Looks like there's questions and there's answers coming there. Okay, good. Looks like things have been answered on the chat there. All right, so that's Bode plots, and so those were the questions online. Let's see, more questions. Okay, good. Kieran is answering a lot of these things. So let me move on past Bode plots now and start talking about amplifiers. And so amplification here, and it looks like I'm kind of out of time here. So for amplification, it basically is a transfer function like Vi to V naught here. And so I think you know amplification already. And so that's why I'm comfortable leaving this lecture without having done amplification yet. Because you can read the book and you've also seen some of this, and I think you know enough to be able to do the problems on your homework assignments that are due Friday, because again, it should all be review. If not, you can go and see office hours and read the book on that. But these are my lectures on amplification here. We're already out of time in this class. So I guess you'll get this lecture on Friday. What should we do about the homework, I suppose? Does anyone want the homework due on Monday instead so you can get the Friday lecture? Who wants that? Okay, there's a yes. All right. So let's, since I haven't done the amplifier here, we're going to get the homework. We're going to make that due on Monday instead. So Monday at 12 noon, just so that I can get a lot of this lecture in here. Now, I'm even comfortable doing it without the lecture, but if you want it on Monday, we'll do it on Monday. because I think this stuff on amplifiers you already have from 16s. But that might not be true, and so that's why we're going to make that homework due on Monday. Okay? I'll put that in the notes on this too. In fact, I'll write that right now in this. So that anyone who wasn't at the lecture can get that. So I'll just say homework number 1. Okay. Due Monday, 9/7. That's a holiday. But that's okay because you're turning it in by Gradescope, I suppose, at 12 noon. Okay? All right, that's it for today, though, and so I will see you all on Friday then. Have a good day.